Hi everyone, please forgive the growling in the background. That's my space heater. My feet are cold and I'm not sure where my microphone is. So, a lot of people wanted a little more guidance with E2 stereochemistry. I've already posted the video on how to use a Newman projection for figuring out an acyclic molecule. If you're working with a cyclohexane, you would need to actually use your chair diagrams in order to figure out what's going on as far as what is anti-periplanar. I wanted to start with a very simple molecule, so I've just started with a cyclohexane and I've just put Lg, meaning leaving group. Right now in this chapter, we're talking about bromine, chlorine, iodine. Later in the chapter, you'll see things like tosylate and mesylates. And what I've done here is I've imagined a chair flip where my leaving group, which was down relative to the hydrogen on this carbon, after the chair flip, it is still down relative to the hydrogen. It has gone from equatorial to axial. So what is it we're looking for when we're thinking about doing E2 on a chair? What we're thinking about is what is anti-periplanar to the leaving group. So what I strongly suggest you do is you build a model of this. And when you build the model, what you're going to see, if you look at a Newman projection down the bond that I've drawn in green, you're going to see that when you do the Newman projection down this bond, you're going to see that what is anti-periplanar to the leaving group is going to be this ring bond right here. And if you take your model and you look down this bond doing a Newman projection, what you're going to see is that it is this carbon-carbon bond that is anti-periplanar to the leaving group. Now remember, when we're doing an elimination, what we're looking at happening is the loss of a hydrogen that is anti-periplanar to the leaving group. So if what we're seeing on our chair is that there is no hydrogen anti-periplanar to the leaving group on the beta carbon, then the reaction won't take place. So if this is a carbon-carbon bond, your base can't pull a carbon, so therefore you're not going to undergo E2 if you don't have a hydrogen anti-periplanar. And what you're going to find if you build your models and you really look at this is you're going to find that whenever your leaving group is equatorial, you're going to be in this situation where what is anti-periplanar on both Newman projections is going to be your carbon-carbon bond. However, if you put this into a chair flip and move that puts your leaving group equatorial, now what you're going to see when you run your Newman projection down this bond is that what is now anti-periplanar to that leaving group is the axial hydrogen on that adjacent carbon. And by the same token, if you turn your model so that you can do your Newman projection looking down this carbon-carbon double bond, what you're going to see is anti-periplanar to the leaving group on this particular carbon is this hydrogen. So what this tells us is that E2 on a cyclohexane, the only reactive conformations are going to be the conformations where our leaving groups are are axial. So when we're doing these E2s, what we're going to see on a chair is that the only way we're going to be able to do an E2 on a chair is when we're in the conformation where the leaving group is axial. This is going to have two consequences. The first consequence is going to be in terms of regiochemistry. The second consequence is going to be in terms of reaction rate or kinetics. And which one is going to be at play depends very much on what the starting material is. So let's look at an example of this conformational effect and how it would affect regiochemistry. So this is the elimination reaction that was on your problem set from November the 2nd, 2018. What we've got here is an isomer of neomethyl chloride, and we're reacting it with sodium methoxide and methanol. As we go a little further in the chapter, we'll notice a couple things. First of all, this is a secondary substrate. Here's the carbon with the leaving group on it. There's 2 carbons and a hydrogen attached to it, so this substrate is secondary. Our reagent here is sodium methoxide, which is a strong, small base. So we predict that this would be E2. You were also specifically told in this scenario that this was an E2. So what do we need to do an E2? Well, we're going to go through the routine that we've been doing so far for E2. We're going to go through and we're going to find our beta protons. So here's beta carbon number 1, beta carbon 2, and we can see that we have beta protons at both of these particular beta carbons. Now, if we're not going to think about the antiperiplanar requirement of the E2, this could seem like a really easy problem, because what we're going to say is, hey, I know that there's two possible E2 products here. The first would be this one. Coming from elimination of this beta proton, forming this alkene product. The other possible product would be coming from eliminating one of these two beta protons and giving us this alkene product. Okay, a couple things to keep in mind. Notice that I've got my alkenes drawn coplanar with all 4 of my bonds in one plane. Same thing here. All 4 of my alkenes are drawn in the plane. I could then go through and say, okay, this particular alkene is 1, 2, 3 tri-substituted. This alkene is 1, 2 di-substituted. The more substituted alkene is more stable. This is the Zaitsev product. And it is the product that I would expect because I've used a small base, and the small base favors the Zaitsev product. But let's double check that the stereochemistry doesn't have anything to do with it. Now, you may already be able to see, depending on how well you're seeing things in 3-dimension, that this hydrogen is on a wedge and this chlorine is on a dash. So these two are clearly anti to each other. And so we could imagine that we could actually do an anti-periplanar elimination right here. But let's double check that on a chair very quickly. So I'm going to draw my chair. I'm going to make this carbon right here where my isopropyl group is. I'm going to draw my up and my down, remembering that since this corner is pointing up, my axial position is pointing up. Since on this position right here, my isopropyl group is pointing down, I'm going to go ahead and put that blue hydrogen up relative to the isopropyl group, my isopropyl group equatorial. Now, I'm going to go around clockwise. My next carbon would be right here. I've got axial pointing down and equatorial pointing up. My chlorine would be down, my hydrogen would be up. Finally, I'm going to skip around 2 more positions clockwise. 1, 2, 1, 2. I'm going to put my axial and equatorial in, down and up. And my methyl group is on a wedge, so it must be up. Now, if I take a look, this proton is anti-periplanar to the chlorine, so I will have no problem eliminating this beta proton with my methoxide base. Losing my chlorine and generating that more stable intermediate. Now, I'm just going to draw it on a chair right now. It actually fits okay if you build a model of it. If you build a model of this, what we actually see is something called a half chair. But for the sake of just seeing what my mechanism did, it is not incorrect to do this. And then if I just count my carbons, 1, 2, 3, 4, I can see that when I draw it, oh, too much pink, hang on. Let me just go around and make these A, B, C, D, A, B, C, D. What I see when I put this on my chair up here is that this is A, B, C, D, making sure that what I've drawn here with the chair, I've transferred correctly to right here. So the major product for this particular reaction is right here. My antiperiplanar reactive conformation gives me exactly the same and shows that the Zaitsev product is able to be formed. Now, problem D on the same problem set looks frighteningly the same, but with one major difference. I've actually given you the diastereomer right here. I've changed this stereocenter from a dash to a wedge. The stereocenter stayed the same as in C. This one is the same, so this is a diastereomer. Same reaction condition, sodium methoxide and methanol. So now we can go in and think about our elimination. Now again, we could count our beta, look at our beta protons. We would have a hydrogen here, and we have two beta hydrogens here. So we could imagine that we have two possible products here, one coming from removing the purple proton, making this product, one coming from removing the blue proton, making this product. Pardon me, this was a methyl. And we could once again say, okay, here I have a di substituted, here I have a tri substituted. This is my Zaitsev, so this must be major. And if I predicted that as my major product, I would actually be completely wrong. And your problem set actually points this out. So this tells us that something else is going on besides just the size of our base and the stability of our product. And what that has to do with is the orientation or the reactive conformation. The fact that the antiperiplanar proton, or that the proton we're pulling has to be antiperiplanar. So once again, let's draw our chairs. Again, my isopropyl group is down, my chlorine is up relative to the hydrogen, and over here my CH3 is up relative to the hydrogen. And again, build some models. I know you hate to, but it's unfortunately what you got to do. If I now take a look at what's going on with this chlorine, what is antiperiplanar to this chlorine is this ring bond and this ring bond. They are carbon-carbon bonds that are antiperiplanar, not carbon-hydrogen. So this particular conformation can't do E2. So if we can't do E2 from this conformation, we're going to have to consider the other conformations. So let's draw a chair flip. Make sure we put everybody in the right place. This carbon right here, the hydrogen is up and axial. The isopropyl is down and equatorial. So on my chair flip, my isopropyl needs to be down but move to axial, and the only way to do that is to rotate it one position counterclockwise. Now I'll go to this position, my axial up, my equatorial down. Chlorine is up in the first chair, so it needs to be up in the second chair, and then make my way over here to my CH3 group. It is still up relative to the hydrogen, and it is now axial as opposed to equatorial. Now, what do we see? Well, if we look here, what we see is that this chlorine is antiperiplanar to the isopropyl group. So that means that we're not going to be able to pull this proton, and this was the blue proton in the previous example. It's not going to undergo an SN2 mechanism via this proton. However, there is another antiperiplanar proton available, and it is the proton that's right here. So this chlorine is now antiperiplanar to this proton. And so this is where our base is going to come in. Our methoxide anion is, if it bumps into this molecule in this conformation, this is when our E2 reaction is going to take place. And so what the product that we're going to get, and I'm going to draw it on the chair just so that I'm not moving a lot and then I can think about things and redraw them. The product I'm going to get from doing that E2 is going to be this product. Okay? And this is going to be exactly the same as this. And if you scroll back to the very beginning, this was the purple product that we predicted. It is the anti-Zaitsev product. It is not the most stable product, but it is the only product that can be formed here, even though it is not the most stable, because this was the only way, the only proton that could be removed when the chlorine was in an antiperiplanar fashion or orientation to be able to do the E2. I'm going to cut you a separate video to talk to you about kinetics, so please stay tuned.